Alright, today we're talking about section 4.1 and 4.2 at the same time. We need to talk about the exponential function. Well, not the. Let's just talk about exponentials for right now. And their graphs. This is a great topic. It's one of the topics I enjoy the most. It is a topic that, when mastered, will help you greatly in your coming courses. So let's start by understanding what a exponential function would be. So exponential functions have the form they are a function, so we'll denote it as f of x is equal to a to the x, where a is a constant. We'll also note that a has to be greater than 0, that is, it has to be positive, and a cannot equal 1. If a equals 1, we just get 1 to the x, and 1 to any power is just 1. So that invalidates that. So the difference about exponential functions is that the variable is in the exponent. So let's look at a basic one. Let's try and graph f of x is equal to 2 to the x. So let's look at a table of values. -2, -1, 0, 1, and 2, and see what happens to 2 to the x. So when we put in x is equal to 2, we'll get 2 squared. If x is equal to 1, we'll get 2 to the first. If x is equal to 0, 2 to the 0, 2 to the -1, 2 to the -2, etc. Now 2 squared is 4. That's simple. 2 to the first is just 2. 2 to the 0 power, remember, anything to the 0 power is 1. And we may have forgotten about our laws of exponents, but I could write 2 to the -1 as 1 over 2 to the first, okay, positive now, and that equals 1/2. Here I could write 2 to the -2 as 1 over 2 to the positive 2, which is 1/4. So these I've just picked to give myself an idea of what's going on. And let's do some plotting. Okay. If x is 0, then y is 1. If x is 1, then y is 2. So we get the point 1, 2. When x is 2, y is 4. If x were 3, we'd be way up here at 3, 8. So from this, I can see that the graph is taking off very steeply, and this is what we call exponentially. And this will allow us to say then something about the end behavior of the graph. That is, if we wanted to talk about the limit as x is going to infinity of 2 to the x, Well, there isn't a bound, there isn't a limit. It is taking off to infinity, so we will say that the limit is infinite as well. Now let's see what happens when x gets less than 0. Okay. When x was negative 1, the graph had a value of a half. When x was negative 2, it became a fourth. If x were negative 3, we would have 1/8. And so now I'm wondering, what is the limit as x goes to negative infinity of 2 to the x? Is there a bounding behavior? Is it taking off to negative infinity? Well, it's certainly not taking off to negative infinity, because every value is staying positive, yet it's getting smaller and smaller and smaller. This is half of that, this is half of that. The next would be 1/16, 1/32, etc. So these numbers are getting smaller and smaller and smaller. And it turns out that they will never actually go negative, nor will they ever actually equal 0. It's going to get extremely, extremely close. It could have 1/2 million, for example. But it will never actually equal 0. So there is a limiting behavior here that is not infinite, and we say that the limit as x goes to negative infinity of 2 to the x would be equal to 0. Which is also why, when we draw this exponential function, we put in a horizontal asymptote. And that horizontal asymptote, the equation of this line, is y equals 0 because of this limit. And let's ask ourselves some questions now that we've done this. What is our y-intercept? Well, when x is 0, y is 1. What is the domain? Well, looking at the graph, I can see that there's not a value of x that I need to exclude. So the domain will go from negative infinity to infinity. That is all real numbers. The region, on the other hand, is different. There are no values of the graph below 0. The very first value that I could pick up is this limiting value of 0, but because it's an asymptote, I will never actually hit 0, so I need to enclose it with a parentheses, and then it will take off infinitely. Okay, let's try another one. Let's do f of x is equal to 1/2 to the x. Again, let's make a table of values. From -2, -1, 0, 1, and 2. 1 half squared, 1, 0, negative 1, negative 2. So we know 1 half squared is 1 half times 1 half, which is 1/4. So that leads to the ordered pair 2, 1/4. 1 half to the first power is simply 1 half. So we have 1, 1 half. Anything to the 0 power will be 1. And again, we have this point 0, 1. This we have to remember our rules of exponents about. Okay? If you have a fraction raised to a negative exponent, that's the same thing as taking the reciprocal of our rational number and now raising it to the positive power. We could do the same up here as well. Take the reciprocal, 2/1, and now it can be raised to the positive 2. So this just becomes 2 to the first, which is just equal to 2. So at negative 1, we have a y value of 2. 2/1 is simply 2. 2 squared is 4. So we have the ordered pair, negative 2, 4. And let's see if we can now graph this. When x is 0, we have the ordered pair 0, 1. When x is 1, we have the ordered pair a half. When x is 2, we went half as much again as that, 2, 1/4. If x was 3, the y value would again be half of 1/4, which is 1/8. So in this manner, our graph, let's make that a little bigger. As we are going to infinity, that is the limit as x is going to infinity of our function now, which is 1/2 to the x. In this case, it's doing the opposite thing that 2 to the x did, and it's approaching 0. So we say that the limit is 0. And therefore we need to put in the horizontal asymptote. Now let's see what happens when we go the other direction. At negative 1, the function took a positive value at 2. At negative 2, it took the value of 4. At negative 3, I hope you'll agree, it would have a value of 8. So if we ask ourselves again, what's the limit now as x goes to negative infinity of 1/2 to the x? In this case, as x is going to negative infinity, the graph is taking off to positive infinity. We could ask ourselves some questions about this graph. We could ask about what the x-intercept is, and in this case we would have none. because of this bounding behavior of y equals 0, this graph will get closer and closer and closer to the x-axis, but will never actually touch it. Therefore, there can be no x-intercepts. The y-intercept is 0, 1. This is the same intercept that we had for 2 to the x. And that's worth noting. Why would that be true? Well, when you let x equals 0, anything to the 0 power becomes 1. And so this is a characteristic of the exponential graphs. We could also talk about the domain. And as I go from positive to positive infinity to negative infinity, there is no value of x to exclude, so the domain is all real numbers, which was the same as 2 to the x. We also have the range. There are no values of the graph below, and the very first value we could pick up is 0. Although, because of this asymptote, it can never actually pick it up. So therefore we'll enclose it with a parentheses, and then the graph will take off to infinity. So we have two very different, well, not so different types of graphs. Here is 2 to the x. Here is 1/2 to the x. They both represent exponential graphs, and we have two types of growth. One is known as exponential growth. Okay, so the graph, this would be known as exponential growth. Because as x gets larger, we're taking off to infinity. This will happen when a is greater than 1. Okay. Here, as x gets larger and larger, the graph is approaching 0, and so this is known as exponential decay. And that it happens when a, our base, goes in between 0 and 1. Now let's look at one more way that we could also do this. So in this case, a is 1/2, and so it is in between 0 and 1, and we get this exponential decay. However, also note, using our rules of exponents, right? This is 1/2 to the first. So I could write this as 2, I could write 1/2 as 2 to the -1, which now if we go power to power, which is what's happening here, I could rewrite this as 2 to the -x. So both of these are equivalent ways of looking at exponential decay when 2 is the base. The other thing that's important to note is if we asked ourselves about one-to-oneness, I would hope we would see that this graph is 1-to-1. Okay? It's getting very, very tight down here, but it is in fact 1-to-1. And the same with our first graph. Although it's getting very, very tight down here, it is in fact 1-to-1. So it's important that we understand how those graphs are and the shape of them, because once we do that, we will need to be able to transform them. Okay? So let's do, so just in summary, exponential growth. When you're doing this, it's easiest to draw in the shape of the graph first. There will always be a y-intercept of 0, 1 if it's your basic functions. Okay. There will always be, for the basic, a horizontal asymptote at y equals 0. In exponential decay, we can again do the same sketch. This needs to be put in our tool kit of functions that we understand about. The graph now looks like this, and so it's easier to actually draw in what the graph looks like first and then label things appropriately. So this is 0, 1. We still have a horizontal asymptote at y equals 0. We can talk about their domains. The domain will always be all real numbers for the basic. And again, the range, because of the asymptote at the horizontal asymptote, y equals 0 cannot be included, but it'll take off to infinity. And the same will happen in this case. Those are the domains, the range. They all have the y-intercept of 0, 1. And if we asked about x-intercepts, again, as a direct result of the horizontal asymptote, there is none. We can look at the one-to-oneness of them, and yes, they are both one-to-one functions. So these are the similarities between exponential growth and decay. Okay. It will be very helpful if you understand these graphs in this way. And now let's recall our transformations. So it's a good idea to understand the graphs basically before you do transformations. So for example, if we had f of x is equal to 3 plus 2 to the x minus 4. This is going to be our goal to graph this. So if we have negative f of x, we could also have f of x plus a constant, or we could take our function and add a constant to it. So these are rigid transformations. And let's recall what they will do. So if you have a function and you take all the y values and make them negative, then this will be a flip over the x-axis. Everything that was up here in a y will now come below. For this one, the constant is wrapped up with the x, and so for that we use the Lars for the left or right shift. And when the constant is on the outside, this is going to give the up or down shift. Okay. So let's try and graph this. Okay. It might be helpful to think about it in this way. This is the same thing as 2 to the x minus 4, and addition commutes, so now plus 3. If that's the case, then this is our constant that's going to move us up 3 units. Here, this minus 4 is wrapped up with the x, and so we'll use Lars. Okay. We are subtracting, so we must be moving to the right. Okay. So we're going to go to the right 4 units. So let's see how this looks. I'll do it in stages so we can look at it. So this is our basic 2 to the x. It's our basic shape. Now, what I need to do is that I need to move this graph to the right 4 units. So every point needs to move over. So that means instead of having this point 0, 1, if I move everything to the right 4 units, I've moved the x's 4, but I haven't moved anywhere in the y. As well as the horizontal asymptote, everything will move over, but this is an infinite line, so we won't have to worry about it. So if it was just 2 to the x minus 4, it would look like so. And now I need to add 3. So everything needs to come up 3 units. And actually, for simplicity, so I don't write on top of this, let's make this minus 3 so we can shift it down. So it'll be clearer for us to see. Okay, so minus 3. Now everything needs to come down 3 units. So there's 2 important points, or aspects. One is this point, so I need to move it down 3 units. So now it's at the point 4, 1 minus 3 is negative 2. But the asymptote will also have to drop. So instead of being at y equals 0 now, it will occur at y equals negative 3. From y0 to y equals negative 3. And now we can just sketch the graph in. Now let's talk about the domain. Okay. So this is 2 to the x minus 4 minus 3. So the domain has not changed. It's from negative infinity to infinity. The range then, well now instead of being 0, our asymptote here is at negative 3, and it will never include negative 3, and it will go to infinity. I hope this makes sense. So it's just our basic graph, the shape that we need to know. We can consider this a parent function shape. We'll shift it to the right, and in this case we moved it down for clarity. And so that will change the range, but the domain does not change. Okay, so there is some practice with that. Now we need to understand what the exponential is. And to do that, let's look at, let's consider a function which is equal to the quantity 1 plus 1 over x, and then I raise that to the x power. So basically I'm taking the number 1 and I'm adding smaller and smaller and smaller parts to it and raising them to that power. So numerically, let's find out how we might consider what's happening as x goes to infinity of this function. Okay? And to do it numerically means to make a table of values. So we could consider things like 1, 2, 3, then we could go to say 5, and then 10. Now we're trying to get to infinity, so let's think about numbers as they get larger and larger. Maybe 10,000. These are clearly nowhere near infinity, but maybe we'll see something happening. For this, I will use a calculator. I wouldn't ask you to do something numerically without a calculator, but I want to show you how this happens. Okay. So, here I will put in the quantity 1 plus 1 divided by x, and I'm raising that to the x power. Okay. I don't know if I can make this lighter so you can see. There we go. Okay. Now from there, I want to start filling in a table of values. Okay. Let me delete out what I have. Okay. So when x is 1, we have a value of 2. When x is 2, we get 2.5. At 3, 2.37. So we're not really moving very much further away at 2 or 3. So we might wonder about 5. 2.48. At 10, 2.59. Very much only incrementally smaller, getting larger. It's getting larger in small amounts. Okay, at 100, it's 2.70 approximately. So we've gone a long way in the x and had very little change in the y. And this is what we're wondering now. Well, is there a limit then? As values of x get larger and larger, if y starts to slow down, is there a limit to it? So we could look at 1,000. And from 100 to 1,000, we're at 2.71. So we might be curious, what happens when I go to 10,000? And at 10,000, I get 2.7181. So we might go in for a very large number and just put in a lot. So at 1 times e times 10 to the 13th power, we have 2.7606. So in this way, we see that there is a bound. That is, as x is going to infinity, we're getting some sort of behavior, and this number is an irrational number, and it is known as e. So it is, this is equal to e. Okay. It's irrational. And e is approximately 2.7182, 81, 83, etc., etc., etc. So this number is bothering me. Hang on 1 second. One plus 1 over x raised to the x power. Okay, I think I typed something in wrong, because that's larger than our limit. So this is 2.7183. Alright, so now this number, e, occurs many, many times in nature and even in applications of banking and such. And this is another reason why we work with e. It's contributed to Leonhard Euler. So you'll see this in your biology classes and chemistry classes as well. And it is known as the exponential function. It is the exponential function. But in the end, it acts the same as the other graphs. Okay. I hope we could agree about this. Using the same logic, e squared, e to the first, e to the 0, e to the negative 1, and e to the negative 2. So since this is an irrational number, let's not even try and approximate it. There is an ordered pair 2e squared. When x is 1, we simply get e. When x is 0, we get 1, because anything to the 0 power is 1. And here, negative 1, e to the negative 1, negative 2, e to the negative 2. You could, of course, write these as 2 as 1 over e squared. And I think from here it's clear that it's positive. Negative 1, 1 over e. But in the end, the graph has the same shape and characteristics. I hope we'd agree that e is smaller than e squared and that e cubed would be getting larger and e to the 4th. So this graph would still be taking off in this direction. So we could label some points. Again, it's easier just to draw the shape in and then label the points to make the true. And I hope this makes sense that 1 over e is larger than 1 over e squared, which will be larger than 1 over e cubed, but it will always stay positive. It has a horizontal asymptote at y equals 0. It represents exponential growth. We have a y-intercept of 0, 1. There is no x-intercepts. The domain is all real numbers. And the range goes from 0 to infinity. Okay, so that's the lecture for today. That's the task. Understand the exponential shapes and the characteristics that go on with all of them, and then translate them.